Okay, we are going to continue our notes on page 7, and we're going to move into the part of our material that talks about making inferences. I've gathered some data, I've analyzed it. Now, what can I say about the information that I've gathered? I want you to remember that we never say that because I notice a pattern, it means that one thing caused another. Okay, so we'll see a lot as we're working today on this idea that correlation and causation are not linked. I cannot say that because these two things appear to interact, that one thing causes another. So that will be a big idea for today. And the other big idea for today is to make sure that I remember the population from my experiment. So if I did an experiment, as we're going to see with this first example, with 500 kids of a specific age group, the only thing I can say is about that specific group of kids. Okay, if I do a study on college students, the only thing I can say is stuff about college students. So two big ideas to keep in mind for today. So on page 7, we're going to start with example 6. Okay, 6 says, psychologists were interested in assessing the effect of commercials on eating behavior in children. They randomly assigned a group of 500 children aged 7 to 11 to two groups. So we're running an experiment here. We've randomized our participants. They're in two groups. After randomization, each child was asked to watch a cartoon in a private room containing a large bowl of goldfish crackers. The cartoon had 2 commercial breaks. The first group saw food commercials during the breaks, while the second group saw non-food commercials, so commercials for games or toys, things like that. Once the children finished watching cartoons, the psychologist weighed the cracker bowl to see how much the child ate. So they knew this bowl of goldfish weighed however many grams or a pound or something like that. At the start of the experiment, once the kid left, they weighed the bowl to figure out how many grams or whatever of goldfish crackers the child had eaten while they were in the room. They found that, on average, children who watched food commercials ate 10 more grams of crackers than children who watched non-food commercials. They repeated the experiment several times with the same results. Okay, so what we noticed was a difference here. Our kids who watched a commercial or watched 2 commercials, according to the experiment design, and saw food commercials tended to eat more crackers than kids who watched non-food commercials. Okay, that's what we're seeing here. That's what they're summarizing here. Children who watched food commercials ate 10 more grams of crackers than children who watch non-food commercials. So on average, this is what we're seeing. What valid conclusions can we draw from this experiment? Bullet 1, or option A, I guess we can call it, the results suggest that a 7 to 11-year-old child would eat 10 more grams of crackers while watching food commercials than they would if they watched other commercials. This one isn't terrible, but I want to point out something here. This is saying that if you are a kid and you're watching food commercials, you're going to eat 10 more grams of crackers. That's not what their results found. They found an average of 10 grams, not that every kid ate 10 more grams. So that means for some kids, they maybe ate 1 or 2 grams more of crackers. For some kids, maybe they ate 20 grams more of crackers, but 10 is our average, not a guaranteed amount. So I don't like this one for that reason. Option 2, the results suggest that food commercials make the people watching eat more crackers than other types of commercials. This is more general, okay? We're gonna eat more crackers if we're watching food commercials. That part's good, but here's the tricky part. It says people. We didn't do an experiment on all age groups or types of people. Our experiment was only on kids age 7 to 11. So I don't like this one for that reason. Our third option here, the results suggest a positive correlation between the number of food commercials and the amount of crackers eaten by 7 to 11-year-old children watching the commercials. This one is really good. Okay, so I like this one a lot. Positive correlations. We're saying there was a relationship here. The other thing I don't like about the second option, food commercials make the people. The commercials don't make the people do anything. What we're seeing is a relationship, but I can't say that the commercials are forcing people to eat more crackers. And then I like that it gives my age group here. I like that it says there's a correlation, a positive correlation between the number of food commercials and the amount of crackers that we're eating. So I can see a relationship here. Food commercials seems to show more crackers eaten, but I'm not like locking that number in. Let's take a look at our last one. So this one looks pretty good to me. Our last one says the results suggest that food commercials can have an influence on the amount of crackers consumed by a 7 to 11-year-old child watching the commercials. So I like that it specifies our age group here, okay? But what I don't like is have an influence, because again, correlation and causation are not the same thing. And that is an important idea, and I want you to write that down. Correlation is not equal to causation. Just because there seems to be a relationship here doesn't mean I can say one thing is causing another thing to happen, okay? I can't do that with an experiment of this design. So my best option here would be this third one, okay? I like that it uses the word correlation. I like that it gives my specific age group of kids that I looked at. I like that it talks about the specific types of commercials that we looked at. That's a good inference to make from that information. Okay, let's take a look at the next page. So on page 8, top of page 8, we're looking at example 7. It says a quality control researcher at an electronics company is testing the life of the company's batteries in a certain camera. The researcher selects 100 batteries at random from the daily output of batteries and finds the life of batteries with a mean of 342 pictures and an associated margin of error of 18 pictures. Margin of the error is another way to talk about standard deviation, and we'll see that a little bit later in this unit. You saw standard deviation in Algebra 1. So that's that idea coming back in here. I get sort of this range that's acceptable, okay? So part A says use the mean and margin of error to determine a range of pictures for battery life. So 342 is our calculated mean, but I would expect my batteries to last for within a few pictures of 342. So within a few, we figured out mathematically would be 18 pictures. So we can figure out what's the lower end of that acceptable range. Our lower bound would be to take our average of 342 pictures and subtract that margin of error of 18. Again, margin of error, same idea as standard deviation. So we get 324 for our lower bound. So within 18 pictures, either way means 18 less for our lower bound. And then for our upper bound, that would be within 18 the other way. So take our mean and add 18. So that would be 360. So I wouldn't expect every set of batteries to last for exactly 342 pictures. But what I would expect is for all of my batteries to last somewhere between 324 and 360 pictures, okay? Anything less than that, I would say, hey, maybe these batteries don't work so well. Anything more than that, I would say these batteries might be an anomaly. Awesome, okay? But anything between 324 and 360, that would be good. Now, part B asks me to draw a conclusion here. So part B says, which of the following is the most appropriate conclusion based on these data? So our first bullet here, all the batteries produced by the company that day have a life between 324 and 360 pictures. Now, remember, I didn't test all of the batteries. I selected 100 at random. And I don't know how many batteries this company makes on a day. So maybe 100 is a lot. Maybe 100 is a very small sample size. Either way, it's not enough for me to guarantee that all the batteries produced by the company on this day are going to definitely have this lifespan of 324 to 360 pictures. Number 2, all the batteries ever produced by the company. Now this is like crazy. First, all the batteries we just talked about is problematic. And then this says ever produced. I selected randomly 100 batteries on one day of production. Okay, I cannot make statements that broad about every battery this company has ever produced. Our third option here, it's plausible that the mean life of batteries produced by the company that day is between 324 and 360 pictures. It's plausible means it's reasonable that I could expect this, okay? This is the same idea as correlation versus causation. So I can't definitively say that all the batteries made by the company on this day are definitely gonna have a lifespan of this amount, but it would be reasonable, it's plausible that I could expect most of them to last about that long. This seems like a good option. Everything in that statement is reasonable. Let's look at the last one. It's plausible that the mean life of all batteries ever, let's stop right here, ever produced. Nope, that's not going to work. Okay, so C is our good option here. So remember, when I'm evaluating inferences, I have to make sure that I'm specifying what my sample was, what age of kids did I survey or interview or experiment with, how many batteries did I select, what day did I select the batteries. Make sure that I'm specific with my sample, make sure that I'm not overgeneralizing, okay, and make sure that I'm not saying that one thing causes it. 8 is a little bit different. This kind of goes back to our sampling methods here. So 8 says a research assistant randomly selects 75 undergraduate students from the list of all students enrolled in the psychology degree program at a large university. She asks each of the 75 students, how many minutes per day do you typically spend reading? The mean reading time in the sample was 89 minutes. The margin of error for this estimate was 4.28 minutes. So they found the mean, and then remember, margin of error, just like our standard deviation that we've seen before. Another research assistant intends to replicate the survey and will attempt to get a smaller margin of error. So they want to bring this number down. What should the second research assistant do to get a smaller margin of error? Anytime I want to improve the results that I have, get more precise data, we always want to increase our sample size. More precise data means I need a larger sample size. So the second researcher should increase the sample size. So they should survey more than 75 undergraduate students. Example 9, in state X, Mr. Camp's 8th grade class consisting of 26 students was surveyed, and 34.6% of the students reported that they had at least 2 siblings. So I did some sort of survey here on just this one 8th grade class, and here's what I found. 34.6% of the students reported they had at least 2 siblings. Now, what we're going to do in our last couple of examples is use our collected information, this sort of compiled data that I have, and be able to extrapolate to different populations. So if I assume that Mr. Camp's 8th grade class is representative of all 8th grade classes, it says the average 8th grade class size in the state is 26, which was his class. Let's say the students in his class are representative students of the state's 8th grade classes. And now let's say there are 1,800 8th grade classes in the state. What's the best estimate that we could come up with for the number of students who have fewer than 2 siblings? Now, in general, I'm not a huge fan of using one class to represent 1,800 classes, but let's say that this is, again, a representative sample here, okay? So if 34.6% of these 26 students have at least 2 siblings, okay? What's the best estimate for the number of students who have fewer than 2 siblings? So one thing to notice here, this was more than 2, right? At least 2. We want fewer than 2. So our at least 2 number, is 34.6%. We want less than 2. So that means I have to find 100 minus this, which would be 65.4%. So I'm looking at 65.4% of my students here, okay? So I wanna know the number of students. So first I need to figure out how many students I'm talking about. A lot of little hidden pieces in this one. So my total students would be 26. It says that's the average size in the 8th grade classes for the state. And we've got 1,800 8th grade classes. I'm gonna multiply those together. And I get 46,800 8th grade students. And I want to know the estimate for how many of them I would expect to have fewer than 2 siblings. So I would expect about 65% of these 46,000 students have fewer than 2 siblings. So I'm going to take 46,800 by 0.654. And that gives me 3067.2. I can't have 0.2 of a student. So 3,067 students. I would expect about 3,000 students in 8th grade classes in this state to have fewer than 2 siblings. Okay, very important that we read our problems carefully because again, they gave me information about at least 2 siblings. What I wanted was less than 2, okay? And then they wanted to know total students and they gave me number of classes and the number of students roughly in each class, the average for each class. For example 10, we're going to go the other way. So for example 9, we took a sample and used that to estimate for the larger population. For example 10, we're going to go the other way. So example 10 says, in a certain country, 15% of the 11th grade students failed a required literacy test. So I have data on the entire country, all the 11th grade students who took this test. Let's say 60 11th grade students were selected at random. So I have information on the entire population, and now I'm going to make a selection out of that population, okay? So 60 of the 11th grade students in the country were selected at random. How many of them would we expect to fail the test? So we know 15% failed. So that means I would expect, if this is a random sample from this population, I would expect 15 of this group to have failed the test. So I'm going to find 15% of 60. And that would give me 9 students. So out of my group of 60, I would expect about 9 of them to have failed this literacy test if 15% of students across the country had failed this literacy test. Okay, so again, the caveat here is I'm assuming this is a random sample. I'm assuming there are no huge variations in portions of the population and how they scored, or that they may have scored differently for other reasons. So as long as this is a representative sample, I should be able to apply that statistic that I know for the whole country to this sample of students. Okay, so those are inferences and conclusions. And we did see, again, our margin of error in there. Just again, make sure that when you're drawing conclusions, you're looking at representative samples, you're careful about your sample population, you read your problems carefully. That example 9 was a little bit tricky for a couple of reasons, and make sure that we never say that because there's a relationship that one thing caused another.